Hello, I welcome you all to this another interesting screencast, and the problem reads rod AB is fixed to a smooth collar D which slides freely along the vertical guide. Determine the internal normal force, shear force, and moment at point C, which is just to the left of the 60 pounds concentrated load. And then I'll say and draw the axial force diagram, shear force diagram, and bending moment diagram. Okay, right. So this problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. First things first, we are going to draw the free body diagram for this particular rod. Right. Okay, we have found MC, which is positive. At the section C, we have found the shear force, which is negative. And then we have found the normal force, which is also negative. So we have the moment positive, the shear force negative, and the normal force negative. So what we need to do now is to start drawing the axial force diagram, the shear force diagram, and the bending moment diagram. Alright, let's prepare the line work. We prepare them in black. This is for the axial. How many cells? 2, 3, 4, 5, 6, 7. Okay, that is fine. I can copy the same one and place it somewhere here, and the same and the other one, I'll place it somewhere there like so. Alright, so let's start doing the work. Let's bring it somewhere here. So let's draw the shear force diagram. Let me just create a boundary here. I create a boundary. Alright, and I create another boundary there. Great. So here we go. This is our axial force diagram. This is our shear force diagram. I think we can move this. This is our shear force diagram. And this is our bending moment diagram. Alright. So we got our A. We move this again. Let me move it somewhere like so. Okay. So positive up, negative down. Okay. So this is how it's going to be for all of them. And we've got our A. Our A. This is our A here. Okay. Then we have a C. Okay, and then we have a B. Okay, ACB. ACB. Great. We're using these differential equations. We have the shear force A prime, I'm calling it A prime, that's the A dx, which is going to be equal to the lateral distributed force, I'm calling Q star, and the axial force itself is equal to the area under the axial distributed force. And we have B prime, which is just equal to Q, the lateral distributed force. Q star is the axial distributed force, Q is the lateral, and V itself is just the area under this lateral distributed force. And then we have M prime, which is just equal to V, and M itself is just the area under the shear diagram. So we're going to use those equations. So let's start plotting. We have at A, what did we find our A is? Our A is alright. Our A is 54.13, and that's a negative. So we'll say our negative will go down like this. Let's say this is our value there, and between A and B, we don't have any axial distributed force, and we don't have any intermediate concentrated axial forces. So because of that, our slope is just going to be 0 up to B. Then later on at B there, they'll add, and then algebraically we'll have a summation of 0. So this is negative, it's in compression. Alright, is that okay? Let me bring this a little bit closer like so. Okay, and then let's go to our shear force diagram. Our shear force diagram, we know that we don't have any initial value at A, therefore our shear will start from 0. We start from A as shear equal to 0 at A, shear will be equal to 0. And we know that our loading, of course, we are looking at the region A to C. Our loading is negative and it is increasing from A to C. It's increasing. And of course, therefore, we expect the slope of our shear slope to be equal to Q, which is negative and increasing. So let's find the area under the load. You just half by 3 by minus 15, and this gives us a minus 22.5. So let's draw that. So it's negative and increasing. So from A we expect a negative and increasing. Well, something like this. Okay, maybe this is too high. Alright, somewhere there like that. And this value here we are saying is a 22.5. Here we didn't indicate the axial force. Axial force, the magnitude is 54.13. Okay, 54.13. Alright, then at C we have a concentrated load which is negative, so we'll have minus 22.5 minus 60. This gives us 82 minus 82.5. Alright, so at this point it will just go down up to 82. Let's say 82 is somewhere there like so. Maybe let's say up to somewhere there. let's say there. We don't exaggerate it so much. Alright, that is okay. So let's move this. So we are saying this value here is 82. This is 82.5. Alright, and then from C to B, let's find what we have. From C to B, what do we have? From C to B, of course, our load is negative. It's negative and it is decreasing. Okay, and therefore V prime will just be equal to Q, which is negative and decreasing, and this magnitude is equal to half by 1.5 by minus 15, and this is equal to minus 11.25, right? Okay, 15 by 1.5 by 0.5, yes. Okay, so now then we have 82 minus 0.5 minus 11.25. When we sum up this, algebraically they give us a 93 minus 93.75, and the slope is negative and is decreasing. So negative and decreasing, we expect a slope like this. Let's say something like this. It's quadratic. Our load is if you look at our load, is a linear function, polynomial of degree 1. Therefore, our shear is going to be a polynomial of degree 2. So this point here, so this is negative and decreasing. This is 93. This is 93.75. 93. And then when we reach at B, of course, the closure takes place. At B, the closure takes place, the two add up. One is negative, the other one is positive, and then we have a closure as usual. Okay, so this is how our shear is going to look. And this is all negative. Okay. Alright. So let's draw the bending moment diagram. Let's bring this one here. Time look clear. Let's write it. This is axial force diagram. This is shear force diagram. This is bending moment diagram. Alright. So let's put it there like so. Right. Now let's draw the bending moment diagram. At A, we have at the initial value, so we need to get the opposite sign of the one that is there, because the internal moment will have the opposite direction of this MA. The MA right now is clockwise, which is negative, therefore we need to take the opposite direction, which is positive. Okay. Because the internal moment, if we are to do a section just to the right of A, we're going to get a counter clockwise moment, which is an internal moment. Okay. Alright. Is that fine? Sure. Great. So we'll have a positive value. Let's say positive value. Let's give it as something like that. Is that fine? Okay. So let's say this one is our value here of 157 pounds feet as our initial value. So we need to now define our shear there. Okay, the Q here, the load Q, we can write this Q in terms of MC. Q is equal to MC plus C, where M is the gradient and therefore our Q, but we know that our C is just going to be equal to 0 because our A is being assumed as a starting point where X is equal to 0 and Y is equal to 0. M is the gradient, and gradient is just a change in Y divided by the change in X, and therefore our Q is just going to be equal to, we are considering from A to C. So a change in Y is just 15 for the distributed force, 15. Change in X is 3. Okay, X, therefore this just becomes a 5X. So this is the function that governs the load. So if you are to make X equal to 0, distributed force at A is 0. And if you made X equal to 3, distributed force at C. X equal to 3 at C, distributed force is what? 15. Okay. So that's the equation that governs our shear. So we are looking at A to C. So our Q is equal to 5x. Okay, and therefore we are going to have our shear is going to be equal to the integral of 5x dx, which is just equal to 5x squared divided by 2, and this gives us just a 2.5x squared, right? Okay, so therefore our shear is just going to be equal to from 0 to 3, or if we are to just say Vx of 3, we can plug in our value there, so it will just be 2.5 by 3 squared. Okay, we want to find shear at C. Okay, alright, so it's 2.5 by 3 squared. Alright, so this gives us a 22.5, which is negative. Alright, this is negative. So subtract from the initial value there of 157. So it's 157 minus 22.5. So let's do that. 157 157.5. So there is a 0.5 here, there's a 0.5. Okay, so 157.5 minus 22.5. So we have 135, right? 157.5, we have a 135. Okay, 135. And when we look at our shear in this region is negative and increasing, and therefore our M prime will just be equal to shear. Okay, the slope will be negative and increasing. So let's do a plot, see how it looks. Negative and increasing, we expect the graph to just fall like this. This is a negative and increasing, right? Like this. Okay, it's a negative and increasing. This value here we said is 135 pounds-feet. Moment there. Okay, this is a polynomial of degree 3. Since our shear is a polynomial of degree 2, our moment is a polynomial of degree 3. Let's now look at the region CB. Let's look at the region CB. The region CB, our shear is negative and it is decreasing, right? So we expect our moment, slope of our moment to also be just equal to the shear, which is negative and decreasing. So we need this magnitude, which is the area under the shear diagram, but we need an equation for shear, which later on we are going to integrate so that we have an equation for moment. So let's look at CB. We have that distributed force. Let's develop a function from there. So this is B, this is C, and we are moving from C to B. And this length here is 1.5, right? This is 15. So if we are to write this in terms of Q, which is mx plus C, the gradient is negative. Change of y is 15 divided by negative 15 divided by 1.5 x. The intercept there, the y-intercept is 15, and therefore this gives us a Q which is equal to, that is from C to B, minus 10 x plus 15. So this is the equation that is governing this triangular distributed force from C to B. Okay, when x is equal to 0 at C, we have a 15, and when x is equal to 1.5, we have a 0 at B. Okay, so therefore our shear in the region CB, okay, our shear from C to B is going to be equal to, the initial value at C is what? So you always focus on your shear force diagram is what? Is 82. I know they are all negative this time around. Now I'm going to subtract them later on when I've calculated the moment is negative. I don't want to include the negative. Okay, but I'll subtract everything else after I've converted this to moment. Our initial value is 82.5. Then I'll say plus the integral of q dx. Okay, and our q is this from C to B that we just found is minus 10 x plus 15 x, and therefore our V is going to be equal to 82.5 minus, when you integrate, 10 x squared over 2 plus 15x. Okay, all right, can I wrap this? So this is now the shear from C to B. Okay, if I wrote it nicely, this becomes a minus 5x squared, it's quadratic, plus 15x, then plus 82.5. So for us to convert this into our moment, we need to integrate it. We know that the area under the shear function, or the area under the shear, is the moment. So moment, therefore, let's integrate that, minus 5x squared plus 15. If you're not comfortable with this, you can always do a section. Okay, you can do a section and find the same things. All right, so again, this moment is from only C to B, okay, which is going to be equal to, again, I'm integrating it as an indefinite. If you want, you can put the integration constants. We are just from 0 to 1.5, just from C to B. So this becomes a minus 5x cubed divided by 3 plus 15x divided by 2 plus 82.5x. When you are doing this, there is no need of putting that constant, right? Remember, when we are dealing with the indefinite integral, we normally say plus c. We don't do this for this particular, when we are working out this, because we are just developing functions from one level to the other, right? So this is the function that defines our moment from region C to B. So now let's plug in our value there. We find the moment, which is the length of CB, which is 1.5. because it's a continuous function from C to B, it is distributed. So a function at 1.5, if you plugged in and you get your calculator, plug in 1.5, you have a minus 5 over 3 by 1.5 cubed plus 15 over 2 is 7.5 by 1.5 squared plus 82.5 by 1.5. So you have a 135. Mind you, this is negative, alright? So this is negative because the shear is negative. So when they sum up these two, so you have a plus 135, which is this one here, okay? And the one that we just found, minus 135, it gives you what? 0, which is a closure. So now we need to do a plot. We've been told that the shear is negative and it's decreasing, and moment also will be negative and decreasing. So a curve that decreases will be something like this. Okay, is it a good one? This is a decrease. All right. So that is about it, and this is positive. This is positive. Okay. So we've done the plots. We have done the plots for both for axial force diagram, the axial force, the bending moment, as well as the axial force diagram, the shear force, and the bending moment diagram. And we've also found the sections at C. We can check them. Section at C, the moment is positive 135 at C. Yes, it is 135, which is at this point here. This 135, and then we have the shear at C is negative, of course. Where is shear is negative? There it is. To the left of the load is negative. To the right is another value to the left of this 60. That's what we are told. And then the normal force is also negative. This is about it. This is really about it, and I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing, liking my channel. Bye bye, and see you in my next screencast.